So now what we're going to do is we're going to start working inside of higher order differential equations. And we're going to start to develop a general theory and some general notation for doing higher order differential equations that will allow us to kind of like really think more deeply about our processes for solving differential equations and using them to do all sorts of different things. Okay, so we're going to start out with this idea of something called the derivative operator. So a vector space CKI is going to be the vector space made up of functions that have kth order derivatives on the interval I. So like for example, C2I is the set of functions that have second order derivatives. That is, you can take the second derivative for every single function that's in the space. And so we've got this vector space, right? And so we're going to define the derivative operator as this linear transformation. And we're going to talk a little bit about the derivative being linear, but as the linear transformation such that dk of cky to c0i, okay? And then dk is going to equal, basically, if you take the derivative of the previous derivative. So like, for example, you've got the first derivative. If you take its derivative, you get the second derivative. If you have the third, if you want to find the third derivative, you take the derivative of the second derivative. And that's how we're going to define the operation. And essentially, we're going to write that dk of f, so like d2 of f is going to be the kth derivative of f of x. So just to kind of define that notation, so d2 of f is just going to equal f double prime, okay, which equals d squared f of dx squared, okay? And you're going to see that this is actually going to kind of come in handy, especially when we're talking about differential equations, right? Because they can kind of get involved, right? So the next thing I want to talk about is I want to talk about the derivative being a linear transformation. So the derivative is a linear transformation, and this is important because we're going to use a lot of the language and the proofs that we've done from working with linear transformations when talking about the derivative. And since the differential equation is basically just the derivative, you're going to see that a lot of that work that we did with linear transformations, with vector spaces, with orthogonal spaces, is all going to apply here to working with differential equations of higher orders. So the derivative is a linear transformation, and let's work on proving that. Okay? So, what do we need to prove? We need to prove that d of f, okay, or if we take if f and g belong to, let's say, CKI, okay, then derivative of f and g, or f plus g, is going to equal the derivative of f plus the derivative of g. Okay? And so, like, for example, if we take, okay, we've got f plus g, and we take its derivative. Remember that derivatives, you can actually take the derivative first and then add. So this is true. F prime plus g prime. Okay? It's just true of derivatives in general. Saw that in your Calc 1 class. Okay? So we're closed under addition. In addition to that, we need to be closed under scalar multiplication. So we want to show if C belongs to, in this case, let's let C belong to some field F, and F belongs to CKI, then D of CF is equal to CD of F. And if you just remember in terms of your rules of derivatives, we know that CF prime equals CF prime, right? Okay, so D of C of F is going to equal CF prime, which equals CF prime, which equals C times D of F. All right? So closed under multiplication. This makes the derivative linear. A linear transformation. Okay, so the derivative is a linear transformation. So everything that we've got for linear transformations, the kernel, the range of the linear transformation, is the transformation 1-to-1, is the transformation onto, do we have an isomorphism? Are the spaces isomorphic? We can answer all those questions utilizing the derivative, just like as if it were just a general linear transformation. Okay, so that gives us the fact that the derivative is a linear transformation. To give you an example of our notation, let's say, for example, that we wanted to know d squared f, okay, and we had that f is equal to x cubed. So d squared f would be the second derivative of f. So d squared f would equal, right, f prime equals 3x squared. F double prime is equal to 6x. So d squared f would end up being equal to 6x. Okay? And we can do that. We don't actually have to put in an f. We can put in the function as it is. So for example, if I took d cubed of cosine x, right? What would I get? The first is negative sine. Second derivative is going to end up being negative cosine. Third derivative is then sine, so this equals sine x. Okay? So that's the third derivative of cosine x. And so that's basically what we mean when we write that d3 of cosine x. We're saying take the third derivative of whatever the function is that we have right here. So now what we're going to do is we're going to bring together some of those derivative operators together with other functions, and we're going to create something called a linear differential operator. And we're going to have this linear differential operator notation, and we're going to denote it as L. And so L is going to equal, it's going to be d to the n, so it's got that derivative operator, plus a1 d to the n minus 1, okay, plus plus a sub n minus 1 d plus a sub n, okay, where a sub 1 through a sub n are functions of x, okay, are functions of some variable x, all right, and that's going to actually allow this to be linear. If you kind of remember when we were talking about this in first order differential equations, and the n is the order of the differential, the linear operator. So like, for example, this is an nth order operator. There we are. So like, what we're going to do with it is we're going to then evaluate, say, for example, functions. So we'll say Ly, and Ly is then going to be dn of y plus a1 dn minus 1 of y plus, and then plus a sub n minus 1 d of y plus a sub n. Okay? And so then we might do something like, hey, does that equal 0? Or does that equal whatever we have L sub y as? Right? The answer, the non-homogeneous part of my differential equation. Whatever it is that we might have, we'll actually go out and we can evaluate that. So let me give you an example. Example of this is something like this. I've got L equals d squared plus 4xd minus 3x. And so let's say, for example, I want to figure out what L of, well, I'll say Ly, right? Okay, so Ly. Now Ly, we've got the second derivative of y, so that's going to be y double prime, plus 4x times, and then this is going to be the first derivative of y, so it'll be y prime minus 3x. So that would be what Ly is if you actually just write it all out, okay? If we choose a value for L, say that we take L cosine x, okay, then L cosine x is going to be the second derivative. It's going to be cosine x, the second derivative of that, plus 4x times the first derivative of cosine x minus 3x. So the second derivative of cosine x is actually going to be negative cosine x. So negative cosine x plus minus 4x sine x minus 3x is what L of cosine x is. Now L is just like, it's a way of defining that we have a linear operator. We actually have, there are lots of different linear operators that we can find. Okay, so if I take another example, if I wanted to write, for example, so we'll take the example of, say, y double prime plus 6y prime plus 4y. for example. We could even like add some kind of function to it if we wanted to. But if we wrote this as a linear operator, it would be Ly equals, and this would be d squared y plus 6dy plus 4y. And that would actually be our linear operator. We could rewrite L as just simply d squared plus 6d plus 4. And that would be L. Okay, so that's kind of like, L is just a notation that we're going to use. We're going to use it quite a lot because it's actually going to end up becoming really handy when we talk about things a little bit more generally.